A more sensitive generating series that can be associated to a combinatorial species is the cycle index series. So let me just write down the definition first, and then we'll try to understand what it means. So given a combinatorial species of combinatorial structures F, we define this cycle index generating series of F. So this is going to be a power series in infinitely many variables, and it's defined as summation n in non-negative integers 1 over n factorial, and then you take a sum over sigma in Sn, and then you count you take f of n, the species applied to the set 1 to n, the f structures on n. Now f sigma is going to be a permutation of fn, and you take the cardinality, and then you write down this monomial next to it, which is x1 sigma 1 x2 sigma 2. Okay, so this definition looks somewhat complicated, so let me just break it down. So firstly, if sigma belongs to Sn, then that means sigma is a bijection from n to n. And so we can talk about f sigma, which is from fn to fn, and that's a bijection too, as we saw last time. And fn superscript f sigma. Now we are back to the notation that we used when we were studying orbits and fixed points and so on. This is the set of fixed points. So the f structures on n that are fixed by f sigma. So f sigma takes s to s. And what about these exponents here? And sigma I is the number of I cycles in the permutation sigma in Sn. So if the cycle type of sigma is going to be 1 to the sigma 1, 2 to the sigma 2, and so on. Okay, so firstly, one of the things is that this series lives in a very large ring with infinitely many variables, and but still it's quite clear there are no issues with adding or multiplying elements, power series in these kinds of rings. Let's just, maybe to get more comfortable with these series, let me point out some specializations of this. So what if I take x1 equals x, x2 equals x3 equals 0. All the variables except x1 I put 0, and x1 I just rename it to x. So let's look at what happens to this function. We get zf of x, comma 0, comma 0, comma 0. This is going to be summation n in n, 1 over n factorial, summation sigma in Sn, fn f sigma, x1 to the sigma 1, so it'll just be x to the sigma 1, 0 to the sigma 2, and so on. Now remember, it's always the convention that 0 to the power 0 is equal to 1. Okay, it's an empty product. Doesn't matter what you're multiplying. So so now this monomial here is equal to 0 if sigma has even one cycle that is of length greater than 1. So this is 0 unless sigma equals the identity of n. And so this sum just becomes summation n in n, 1 over n factorial. Then the fixed points of fn under the identity map is all of Fn. And so this is nothing but summation n in n Fn x to the power n over n factorial, which is the generating series of the species F. Slightly more interesting. Well, this is already interesting in the sense that you can recover the generating series of F from the cycle index series. But here's something more interesting that you can do. Put xi to be x to the power I. So x1 is x, x2 is x squared, x3 is x cubed, and so on, for all positive integers I. Then, if sigma is a permutation in Sn, what do you get? Then sigma 1 plus 2 sigma 2 plus n sigma n, well, no, we don't know where this stops. Sigma 1 plus 2 sigma 2, this will be a finite sum. This is going to be n. This is the number of 1 cycles plus 2 times the number of 2 cycles plus dot dot dot. That's going to be n, the total number of elements. And so this ZF of x1, so now we are writing x squared, x cubed. Okay, so remember what this was. Let's just copy it down. Sum n in natural numbers 1 over n factorial. N in non-negative integers 1 over n factorial. But what we saw is that if sigma is in Sn, then that means that x to the sigma 1. So this product here, x1 to the sigma 1, x2 to the sigma 2, this becomes x to the sigma 1, x to the 2 sigma 2, and so on. So x1, so x to the sigma 1, x to the 2 sigma 2, x, and so on. This becomes just x to the power n. So we can pull this x to the power n out, and we have sum over sigma in Sn, and then we have f of n, f of sigma, the number of fixed points. So the coefficient of x to the n over here is 1 over n factorial sigma in Sn Fn f sigma fixed points. But by the Burnside theorem, this is or Burnside's lemma, or the orbit counting theorem, this is n in n x to the n, and the coefficient is the number of Sn orbits on Fn. Okay, so it's now an ordinary generating function, and what it counts is the number of Sn orbits on Fn. We are thinking of Sn as a permutation group on Fn. So let's step back a bit and understand what is the meaning of Sn orbits on Fn. Maybe it's better to work with an example. Consider F to be the species of graph structures, simple graphs. So if we take G of 3, so we have 3 points, 1, 2, 3, and we have to see what are all the different graph structures that we can put on them. So one is that you just put the discrete graph structure. There are 3 points and there are no edges. Then there are three graph structures with one edge. Let me just. So what you can do is you can put the edge either between 1 and 2, or between 2 and 3, or between 3 and 1. Then there are three graph structures with two edges. Maybe I should stick to one way of writing the numbers. So there are three graph structures with two edges. So you can put on 1 2 2 3, or 2 3 3 1, or 3 1 1 2. The three graph structures with two edges, and finally there's one graph structure with three edges. And so totally there are six graph structures. And now the question is, which of these are in the same S3 orbit? So to say that two graphs are in the same S3 orbit means that I can relabel the vertices of this graph using some permutation of n, so that I can go from one to the other. So for example, if I relabel here 3 to be 1, 1 to be 2, and 2 to be 3, then these are isomorphic. So under the permutation, 1 goes to 2, 2 goes to 3, and 3 goes to 1. And these are also isomorphic under the same permutation. But anyway, so so there are three S3 orbits. So the S3 orbits in the species of graphs, these are what are called isomorphism classes. The Sn orbits are isomorphism classes. Sometimes they are called types. So there are different types of graphs. In this case, I only looked at three vertices so that I could enumerate everything. In this case, it turns out that if two graphs have the same number of edges, then they're isomorphic. But that's certainly not the case the moment you look at graphs with 4 or more vertices. So in general, by definition, for a species f, and finite sets u and v, S in fu and t in fv. So S is an F structure on U, T is an F structure on V, are said to be isomorphic or of the same type if there exists a bijection sigma U to V such that F sigma takes S to T. And so what we have is that Fn mod Sn is the set of it's called isomorphism classes of F structures on N, or types of F structures on M. This generating series that we have here, Z of F, evaluated x squared, x cubed, you can think of it as a generating series in one variable x. So f tilde x defined to be zf x squared, x cubed is called the type generating series for f. And of course, what we've seen is that this is some in non-negative integers cardinality of fn mod Sn, that means the number of types of f structures xn by n factorial. There are some species for which it's fairly straightforward to enumerate the number of f structures on n, for example graphs or directed graphs, but it is very difficult to enumerate the number of types or the number of isomorphism classes of f structures on n. Okay, it's very hard to figure out how many graph structures are isomorphism classes of graph structures are there with n vertices. Just like the generating series of a species, the cycle index series is also computed using only one specific set of cardinality n, namely the set of integers from 1 to n. And the point is that you can use any set of cardinality n to compute the nth term of the generating series. The reason is the following. So suppose u and v are finite sets and there's a bijection between them. So suppose alpha u to v is a bijection of finite sets. Then there's a bijection between the permutations of u and the permutations of v determined by alpha. Sigma goes to, so if you have a permutation of, so if you have alpha from u to v, and if you have a permutation sigma from u to u, well, you have alpha from u to v, you can fill this arrow here, and what you get is the permutation alpha circle sigma circle alpha inverse is a bijection from permutations of u to permutations of v. And if you now apply f to these things, then so what I want to say is that S belongs to fu is fixed by f sigma if and only if f alpha of S belonging to fv. So S is an f structure on u, f alpha of S is an f structure on v, is fixed by f of alpha circle sigma circle alpha inverse, which is the same as, of course, f alpha circle sigma circle f alpha inverse. So what we have is that if u and v are of the same cardinality, then you can try to compute the cycle index series using u. So the term you get is 1 over u cardinality of u factorial sigma belonging to su fu f sigma fixed points and then x1 raised to sigma 1, x2 raised to sigma 2, etc. Well, that is going to be the same as 1 over cardinality of v factorial. Well, u and v have the same cardinality, so these are the same. And now we can take sigma belongs to SV, but these sigma belong to SV are all of the form, maybe I'll call it tau belong to SV. These tau are all of the form alpha circle sigma circle alpha inverse. And then we are taking the FV invariant points of F tau. And then x1 to the tau 1, x2 to the tau 2, and so on. But this set here is just F alpha of the fixed points of Fu under F sigma. And so this cardinality is equal to this cardinality. And so here you have equality. And so whether you compute the nth term of the cycle index generating series using the set 1 to n or any set of cardinality n doesn't matter. And in particular, if f is a species, so maybe you can write this down as a small theorem, that the number of isomorphism classes of F structures on U depends only on the cardinality of U. So in fact, in this type generating function, we could have replaced n, the set 1 to n, by any set of cardinality n and computed the type generating series. So now let's go ahead and try to compute some cycle index series, maybe for some species. Let's start with the really easy examples. So examples of cycle index series. So maybe the easiest example is the empty species. Everything is empty, and this is just going to be the function 0. The empty set species, which has only one of the empty set is singleton and one of any other set is 0. This is going to have type generating function 1. Let me just remind you here what the type generating function is defined as. So it's sum n in n, 1 over n factorial, sum sigma in Sn, number of fixed points of Fn under F sigma, and then we have 1 to the x1 to the sigma 1, x2 to the sigma 2. Right. So in this case, there's only one n for which there's a non-trivial term, and that term is 1. We are taking the n equals 0. What about zx? In this case, there's only one non-trivial term, which is for n equals 1. And in that case, the only permutation of S1 is the identity permutation, and it has one cycle and no other cycles. And so we get just x1. Okay, so these were fairly straightforward. Now let's consider L, the species of linear orders on X. Okay, so how do we think of L on a set? So if S belongs to LU, then we can just understand L completely by arranging the elements of U in increasing order with respect to S. P the elements of S arranged, elements of U arranged in increasing order with respect to S. So S is a linear order, we can just arrange all the elements in increasing order. And if sigma is a permutation of U, SU or perm U, then sigma S is going to be I should say sigma square brackets S is going to be, will have by definition U sigma 1 sigma U1 less than sigma U2 less than sigma UN, sigma of S. So this, this follows from the definition of transport of structure for linear orders. In the transport of structure, if we have X is less than Y in S, this is the same as saying that sigma X is less than sigma Y in sigma S. This is how transport of structure is defined for linear orders. And so what you see is that sigma S is equal to S if and only if sigma is the identity permutation. The only permutation, in other words, the only permutation sigma which has any fixed points whatsoever is the identity permutation, and all other permutations will have no fixed points. So if we take f of u fixed points under f of sigma, then this is going to be f of u, obviously if sigma is the identity of u, because f sigma will then be the identity of fu, but this is going to be the empty set otherwise. So what we get is ZL of x1, x2. This is going to be sum n in n, 1 over n factorial. Now there's going to be only one term sigma in Sn which will correspond to the identity, and that will just be f of n. So L of n, which is n factorial. And the identity will have x1 to be equal to sigma 1 to be equal to n. It will have n1 cycles and 0 cycles of any other size. So you will just get x1 to the n. So these cancel off, and what you get is 1 over 1 minus x1. So the cycle index generating function for L is just 1 over 1 minus x1. Now let's compute the cycle index series for the species of permutations. So the main computation to be done here is to compute the number of fixed points of fu, S of u, under the action of S of sigma for some sigma in terms of its cycle decomposition. Some bijection sigma from u to u, some permutation sigma of u. Now the main thing to note is that S sigma of S, so if S is in SU, so S is just a permutation on U, this is little s, then S sigma S of sigma X is sigma Y if Y is S of X. So this is how S sigma of S is defined, the transport of structure S under sigma. Another way of thinking about this is that if, let's just think about this visually, that means that if S of U goes to V, so if I have U and under S, U goes to V, then and under sigma, U goes to sigma U, then under S, V goes to sigma V. Okay, what this means is that suppose we have a cycle for sigma. So suppose this is a cycle for sigma, then we can draw it like this: U1, then under sigma it goes to U2, under sigma goes to U3, and so on. UN, UK, and that goes back to 1. And suppose we say that let Vi, then what we are saying is that S of U1, will go to sigma of S of U1, and so on. What this means is that if S is fixed by S is SU, it's fixed by S sigma, then S takes cycles of sigma to cycles of sigma. Okay, so in particular, S could either it could permute cycles of the same of sigma of the same size, and within each cycle you can it could rotate the cycle by as many turns as the size of the cycle. And therefore what we get, and this is a calculation that similar calculation we've done before, that this is product over I in P, I raised to sigma I factorial, where sigma I is equal to the number of I cycles in sigma. And so what we get is Zs of x1, x2 is equal to sum n in n, 1 over n factorial. And now we are looking at the number of elements. Well, okay, so let's just write down first. S of n, S of sigma, x1 raised to sigma 1, x2 raised to sigma 2. Now let's break this up into a sum over cycle types. So what we'll do is we'll take sum over all partitions alpha of n. So alpha is 1 raised to a1, 2 raised to a2, and so on. And then the number of elements with cycle type alpha. So that we've already seen is going to be 1 over n factorial product I raised to ai factorial. We've seen this in an earlier lecture. And then we have the number of fixed points which we just computed, and this is product I raised to ai factorial again. And then we have, of course, product xi to the power ai. And if you so there's this tremendous cancellation over here. And so what we just get is sum over n in n, sum over a1 plus 2a2 plus dot 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 is equal to n product xi to the power ai. Well, now this sum is over all non-negative integers n, and this sum is over all non-negative integers a1, a2, a3 with a condition on that. But we can just make this an unconditional sum over all non-negative integers ai greater than 0. So we, or maybe just to be clearer, I'll say a1 in n, a2 in n, and so on. And then we have product xi to the power ai I in p. Using distributivity, we can write this as product I in p summation ai in n xi to the power ai, which becomes product I in p 1 over 1 minus xi. And so what we get is zs of x1 x2 is the infinite product I in p 1 over 1 minus xi. Now in this calculation here, I have done a lot of interchange of infinite sums with infinite products. In fact, I have here an infinite sum over infinitely many indices, but really you can think of that just as a sum over a countable set. And one needs to be a little careful with formal power series here, but I think if you think it through, you'll see that all these steps are valid. I will not get into this issue of justifying these steps. They certainly work perfectly well when you work with formal power series in infinitely many variables. Let's compute now the cycle index generating function for the species of sets. So recall that E is the species where E of u is just singleton u for every finite set u. And we want to compute its cycle index generating series. So ZU by definition is sum of n greater than or equal to 0, 1 over n factorial summation, let's say sigma in Sn, and then we must take just E of u, that's just a singleton set, E of sigma, fixed points, well that's still going to be singleton, and then we have product over I greater than or equal to 1 xi to the power sigma I. So this is just 1 and we don't need to bother about it. What this becomes is summation n greater than or equal to 0, 1 over n factorial, and this we can organize the permutations by cycle type. So this becomes a sum over all permutations with cycle type, say with sigma 1 1 cycle, sigma 2 2 cycles, and so on. So if you have a permutation of in Sn, then sigma 1 plus 2 sigma 2 you could have at most n cycles, so plus dot 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 n sigma n is going to be equal to n. And then the number of permutations with this cycle type is just n factorial divided by product over I greater than or equal to 1, I raised to sigma I factorial. This is something we've seen before. And then we have product I greater than or equal to 1, xi to the power sigma I. But this is nothing but what we can do is we can forget about what n is. This is just a sum over all sigma 1 greater than or equal to 0, sigma 2 greater than or equal to 0, and so on. And this n factorial cancels out with this n factorial, and what we get is product I greater than or equal to 1, xi to the power sigma I divided by I to the power sigma I factorial. Now, using the distributivity of multiplication over addition, this just becomes product I greater than or equal to 1 summation sigma I greater than or equal to 0, and what we have is xi by I to the power sigma I divided by sigma I. Now you will recognize this inner sum as just the exponential of xi by I, which is nothing but some exponential of the sum I greater than or equal to 1 xi by I. If you wish, you can write this as exponential of x1 plus x2 by 2 plus x3 by 3, and so on. So you see that the cycle index generating function of the species E is just exponential of x1 plus x2 by 2 plus x3 by 3. And we can check that, E of x, well, E of x is just supposed to be some ze of x1 comma 0 comma 0, just x comma 0. This is indeed just x of x, and E tilde x is supposed to be ze of x comma x squared, and so on. So this is x of summation I greater than or equal to 1 xi by I, but this is the same as x of log of 1 over, not x sub I, it's x to the power I by I, which is just summation log of 1 over 1 minus xi, which is just 1 over 1 minus x, which is just 1 over 1 minus x. Both are exactly as we expected, because we know that there's only one E structure on any set, and there's only one type of E structure on every set.